SFPE seminar this month. Today we are very pleased to have Dr. Nieves Fernandez-Anez to give us a lecture on the topic of dust explosions of solid biofuels, current needs and future trends. And Dr. Nieves Fernandez-Anez was a postdoc here with us at Imperial College London. So basically, she just came back home today, and she's currently an associate professor at Western Norway University of Applied Science. And let's welcome her.
Thank you. Yeah, so, well, I hope that my voice stays for all the talk, but if not, I have some videos there that we can do. When you asked me to do this, I was thinking if I should go back to the cellular automata and small fires and this, which is what I did here. But I am going back a bit to my beginnings. So my thesis was on dust explosions. There is a really good big group in Norway, in Bergen, which were pioneers in dust explosions, and now I have contacted them, and it looks like we're doing things and everything's going on. So I hope that this is gonna be in my future too. I was thinking on the talk, and I have decided to do something from the beginning till where we are now. So there is not a lot of present research. I'm gonna give you some tips. I'm gonna give you. I just want to put here how I see things and how I think that things are gonna go, or I expect them to go. So I'm gonna start from what are we speaking about, because we are speaking about dust, but it is not that easy to define a dust. If you go to the dictionary, you have dry dirt in the form of powder that covers surfaces inside a building, or very small dry pieces of soil, sand, or other substances. Definition number 2 is very small dry particles of earth or sand. Definition number 3 is a fine powder which consists of very small particles of a substance such as gold, wood, or coal. This is like, okay, so what? So in industry, it is normal to use this definition. Dust is any solid particle of less than 0.5 millimeter which can be deposited by its own weight, but can also stay in suspension for some time. And this is more or less worldwide agreed, but keep this in mind because we're gonna discuss this definition afterwards. And this is the one that you can find in the books probably. And what is a dust explosion? A dust explosion is an uncontrolled rapid combustion propagating itself with generation of heat and gases at high temperature and pressures. It is important that you know about the fire pentagon. Everybody knows about the fire triangle, which is the typical one, but for dust, we have this pentagon, and this is the one that we work with. You have to have, for having a dust explosion, you need to have a fuel, combustible dust, mixed with air and the oxygen of the air, dispersed in the air, then you have an ignition source, and if it is confined, you are going to have a dust explosion. The confinement is important because if the other 4 things happen without the confinement, you normally have only a flash fire. But if you have the confinement, then you have an explosion and will develop into domino effect. So what do we know about dust explosions? The first, this was something that my thesis supervisor always spoke about, and I really like. The first dust explosion that is documented happened in Turin in 1785, and it was in a bakery. There was a guy that was baking the bread or something in the basement, and because of the flour that he was using, an explosion occurred. Then somebody thought, is that true? Because if you don't know anything about this, you will probably never believe that flour would cause such a big explosion. Then we have our, let's see if this works. It is happening. Notice, guys?
Yeah.
So, is it still happening? The reality is that we are going to see some statistics afterwards, but I'm sorry that the two videos that I have are so close, but it didn't fit anywhere else. I put a video here. This is my, I don't know if I can say this, one of my favorite explosions somehow. It happened in 2008. It was in a sugar refinery, and there was 14 people killed and 36 injured. So it was very, very big, and it made a lot of changes on standards. So this is just so you have an overview of how an explosion occurred.
In 3 100-foot tall silos and then conveyed into packing buildings where it was packaged for distribution. Granulated sugar was also converted into specialty products such as brown sugar and powdered sugar. Sugar was transported by a complex system of bucket elevators, screw conveyors, and conveyor belts. During this process, sugar spilled onto floors throughout the work area. In places, sugar also contained fine particles which became airborne. In addition, hammer mills were used to crush the granulated sugar into powdered sugar, creating even more dust. The machines were connected to a dust collection system, but it was undersized and in disrepair. And it was not connected to the bucket elevators and conveyors. Significant amounts of sugar dust escaped into the work areas. Workers routinely used compressed air to clean packaging machines, further dispersing sugar dust throughout the buildings. Over time, large amounts of dust accumulated on elevated, hard-to-clean surfaces, such as ducts, beams, and light fixtures. These surfaces were not cleaned often enough to always keep the dust below hazardous levels. In the tunnel beneath the sugar silos, granulated sugar flowed through chutes onto a long steel conveyor belt. From time to time, clumps of sugar would become stuck in one of the chutes, blocking the flow of sugar on the belt, spilling sugar onto the floor and releasing dust into the tunnel. But the tunnel was large and ventilated, so this airborne dust did not build up to explosive concentrations. In 2007, the company enclosed the conveyor belt with stainless steel panels to protect the sugar from possible contamination. It was not equipped with a dust collection system. As a consequence, sugar dust would now be trapped inside this enclosure. On February 7, 2008, clumps of sugar were found blocking one of the discharge chutes. Sugar from the adjacent silo likely spilled off the moving belt. Dust likely accumulated to an explosive concentration inside the enclosure. At about 7:15 p.m., the sugar dust contacted a nearby ignition source, likely an overheated barrel, and exploded. This primary explosion blew apart the enclosure and vented into the packing building. Accumulated sugar was lofted and ignited by the advancing fireballs. The dust clouds fueled a chain reaction of secondary explosions, which swept through the buildings. Concrete floors buckled, releasing tons of granulated and powdered sugar into the flames. Emergency evacuation drills had not been conducted, and the explosions had cut the power to much of the interior lighting. In the maze of darkened and damaged stairwells and passageways, workers desperately tried to flee the growing inferno.
It was just to give you a scale of how things happen, and then it really happens. And normally it is because they were blowing air and forming dust clouds. They were not collecting the dust. There are always some things, and still in 2019 it looks like many people hasn't learned from all this. So we're trying to be more open with what happened. There is a really cool website called Dust Safety Science, from a former PhD student from Halifax, and he releasing yearly combustible dust incident reports. He hasn't done the 2019 yet, complete, but it is 2019 mid-year. And these are the numbers. I also work in wildfire, so it is a bit difficult to scale things up. But I feel that 12 fatalities in 6 months in dust explosions in industries in 2019 is way more than what it should be, right? Because we know everything. Everything is there for us. So, yeah. The materials normally involved in these explosions are the ones that you can see here. It doesn't vary a lot from year to year. Maybe food products increase and then decrease. There was a lot of research there for a couple of years, but at the end wood products, metal and food products are the 3 big groups that are the most dangerous one. So what? How can we avoid these risks? We speak about, are you familiar with these charts? The risk chart, right? Depending on the consequences of the explosion and the probability of happening an explosion, you can categorize the risk of your explosion. And then if you are in the dark green in this screen, or light one, it's okay, the yellow one, and the other you should never be. What happens if we are in the red one? How can we solve this? There is something called the prevention and protection philosophy, and for dust explosions, what we normally do is that we try to reply to these questions in this order. Is it possible to avoid the dangerous material? Can you use other materials? Are there any alternative methods that can help on reducing dust escapes? Can the dust accumulation be avoided by ventilation or cleaning or different ways? Can the dispersion of dust be avoided by controlling the dust deposits? Can the primary ignition be ignited? Can we control the ignition sources by inerting the spaces? If there is any term or anything that you want clarification on, just stop me, because I'm sorry. Can the incipient ignition be inhibited? This is called suppression. Or can the effects of explosion be limited by venting, resistant constructions, or isolation? Now this first group is called the prevention measurements, and you always have to try to do prevention, because prevention means to avoid the occurrence of the explosions. But the reality, and this is something that I always try to teach to the students, is that you can't avoid everything. And sometimes an explosion is going to happen, and this is something that everybody has to live with. But we have to try that if an explosion happens, the consequences are the least that are possible. And for this, we design protection measurements that are to minimize the damage caused by the explosion, right? So if we go back to this chart, what we do with protection is that we move in this direction to make the consequences smaller. And if we do prevention, we reduce the probability of the explosion. So we can move from a very harmful area to, well, an explosion happens, and it's okay. To prevent, normally we do three things. We eliminate the risk related with the fuel, we eliminate the ignition sources, or we eliminate the oxygen by inerting the atmosphere. And for protection, the main 4 ways of protection are suppression, venting, pressure-resistant constructions, and isolation, which you have the drawings there of more or less which one of them do. It is important to know that detailed experimental and theoretical studies of physical and chemical aspects are essential, and you always have to test your material and your facility, because what I have is never going to be exactly the same that my neighbor has. So what should I know before starting with all this? What we should know is that we have to do a characterization of fuels. The dynamics of dust explosions is that an explosion occurs in 3 steps in very quick succession. It is very difficult to see transitions and to see. It is the volatilization, gas phase mixing of fuel and oxidant, and gas phase combustion. Many organic dusts allow a flame to propagate through the cloud in a manner similar to the propagation of flames in premixed fuel oxidant gases. And it is not only this, there is something called the domino effect. Domino, it's very the Spanish pronunciation, but domino effect, right? Because you have a primary explosion inside an equipment, in a piece, you have a leak, something like this. But the fact is that normally you have something like the facility for the imperial sugar explosion that we have seen. Yes, you only have this, but then you have an explosion and you have all this layer of sugar, and then with the wave you put into suspension the dust, and then you have a new cloud and a new explosion, and everything moves, and it can be really devastating. So the concepts that we should know from our dusts are general characteristics, chemical composition of the dust. Not gonna stop a lot in this, but again, if you want to go deeper in something, just tell me. Chemical composition, by knowing volatiles, ash, fixed carbon, moisture content, carbon content. There are a lot of studies that I'm gonna speak a bit later about this that show a big relationship about this. Then we have the particle size. Because the smaller the particle size, the higher the risk, right? This is something that everybody knows. And we will come back to this too. Then there are three groups of parameters that are the ones that we normally, back in Madrid I used to work in a lab that was characterizing this kind of dust for industry. So these were the parameters that we were testing for them, because if you know this, you can, with initial sensibility, you can design all the prevention measurements in your facility. It refers to every characteristic of the dust related to its easiness to ignite. There are three. The minimum ignition temperature, which is the minimum ignition that you need to ignite, a dust, a cloud, or a layer. So you have two different ones. These are sketches of the experiments. Lower explosivity limit that everybody knows, and you have this 20-liter sphere or 1 cubic meter sphere to determine, and the minimum ignition energy that you can determine with the Harman tube. Then we have explosion severity. The explosion severity allows the evaluation of the explosion consequence. You use it to design the protection measurements, because if you know the maximum pressure that your explosion is going to have, you can design a vessel. If you are sure that your explosion is never going to be more than 8 bar, if you are sure that your vessel is going to always resist 8 bar, then it doesn't matter what happens inside the vessel, it is going to resist. And the limiting oxygen concentration, which is used to design the inerting concentrations for the vessel silos. And then you have thermal susceptibility, which determines the thermal behavior and self-combustion tendency. We speak about the Matthias index, which is you mix your dust with H2O2, and you see if it oxidizes or not. Temperature of flammable volatiles, we just check if the volatiles emitted by the dust are flammable or not, and at what temperature they are flammable. And then we use thermogravimetric analysis and differential scanning calorimetry analysis. These have been used for a long time. They are still used. You can get a lot of parameters from them. They have a main problem, which is that the sample that you can test here is really small. And for dust, where the particle size is so important, you have to always reduce it to do this test normally, and it is a bit. But with some of these parameters, my former supervisor created this graph. Can you see it? In this axis, you have the oxidation temperature, which is you can do it with a thermogravimetry analysis, and the activation energy. And you have different areas: low risk, medium risk, high risk, and very high risk for self-ignition. So depending on the area, you can put there the samples, and depending on the area, you can see the risk of self-heating and self-ignition of the samples. Here you can see, these were the samples of my thesis. So you can see, or what I think that is interesting for many people is that I had 2 coals, for example, and both of them are in the high risk area, which is expected. But in the very high risk area, I only had sewage sludge, which was, I didn't expect good chips to be much less then there was done sewage sludge. But yeah, I mean this was empirical.
How do you have dust from sewage sludge?
We have in Spain it is not typical but common to do a thermally drying of sewage sludge, and then you get round pellets. Mhm. Mhm. So we studied. This is another project that we can speak also. We studied how different origins and different seasonalities were influencing the explosibility of sewage sludge by this, because they are transporting it and they are. There was a big explosion in Catalonia in, I would say 2010 or something like this. I don't remember, in a thermally drying sewage sludge plant. So okay, yeah, all this was theory, all this was to set, but what do we really know? So we are in all this era of what do we have to use? Fossil fuels, biofuels, one, the other, both of them, should we combine, should we? I'm not here to convince you of anything. I'm very fan of the biofuels and biomass, but yeah, I am a mining engineer also, so everything is fine. The reality is that according to the BPE Statistical Review of World Energy, the reserves of coal are gonna be exhausted by year 2169. Is this true? There are other studies that say that we will peak coal for production at this year, but we are going to continue producing for some more hundred of years. We don't know, but the situation is not good. So the reality is that everybody is looking for solutions. It doesn't matter. You can speak about biofuels, you can speak about renewables energy, you can speak about many other stuff, but there is a lot of investment and a lot of people looking for solutions. What is better for the environment? What are we gonna do? What is better for economy? How will forests be in 100 years? We don't know. Like all this, I was going to put more questions, but I thought that it was a bit of just me going crazy. Because I'm kind of worried about all this, but in reality, nobody knows any of this. Like we can speak about this for years if you want, but we just have hypotheses. We don't know what is going to happen. We're speaking about the fossil fuels are going to end, and they're coming to an end, and we're not going to have them anymore. Is anybody 100% sure of that? Because I don't think so. I have been reading a lot. Or is the future to do energy crops and just live with this? Is the future of just do offshore wine mills? I don't know. There are many options there. The fact is that we need to keep on moving with this. We need to know what, when, how, where, and who is going to do all this. So we focus, I started my thesis in 2012, and we focus on biomass and waste and this as an energy source. And I still believe on this. I think that, or I know that biomass is key in all the future scenarios that the European Union is studying and is speaking about. And biomass is always present in everything that they are publishing and reporting and saying. Forest, energy crops, waste, and all these materials processing will be essential to ensure the energetic supply that we need. More researchers are working on developing new materials or combining existing materials and working in this line. What I feel that is key and what I feel that many people are trying to do is to substitute coal by biomass, but with a lower possible investment. So we speak about things like co-firing, that they are mixing coal with biomass or with waste or with different things in a way that they can still use the same facilities that coal had, so they don't have to make a big investment. But what? How are we doing this? And now I'm moving to the field of flammability. Now, it is asked, how is it going to change? dust, dust, energy, energy. The same has to happen. Well, if you go and you check the difference between biomass and coal, you can see all this list of things. If you go to the Van Krevelen graph, you can see that it is not the same, right? It is not in the same place of the graph, it is not in the same numbers of the table. So what? I'm gonna start with coal and I'm gonna be very brief. But if you guys want to go into knowing anything about dust explosions, start by coal because all the knowledge is there. I just didn't have a lot of time, so I'm just gonna go. What is coal? Coal is a black or dark brown rock consisting chiefly of carbonized plant matter, found mainly in underground seams and used as fuel. There are many ways of categorizing coal. There are many studies on this for several years. Everybody has been studying coal. What we use is that we classify coal by their rank. You have these 4 types, yeah? Lignite is just the following step from peat. So it goes, maturity goes in this way. Lignite, subbituminous, bituminous, and anthracite. This is very nice, you know, obviously you have less anthracite, they have better things, worse things. I don't know a lot about why they use one or why they use another. What I know is that there is also a correlation for flammability. The most ranked ones, the most evolved coals have less tendency to ignite. This is something that somebody saw and they started checking it. And it was very difficult because people didn't believe that coal was exploding. They thought, so for a lot of years, they thought that the only way of having an explosion in a mine was the methane. And when people started speaking about dust explosion and the coal, they didn't believe on it. So there was a lot of investment and a lot of resources for this. And they saw that there are several parameters that influence flammability. Volatiles and ash, the higher the volatiles content, the lower the ash content, the more flammable the materials are. Moisture, the higher the moisture content, the more difficult it is for it to ignite. This is obvious. Particle size, the lower the particle size, the highest the tendency to ignite. And they discovered something very interesting, which was compaction. By compacting layers of coal, you reduce the tendency of self-ignition, for example. And this was, you reduce the oxygen access. Are you thinking? Yeah, you put the face, Francesca. You said.
Me?
Yeah.
No, because I heard from other presentation that when there's more pressure, it's easier to get ignited.
Yeah.
From like Francisco and other people.
Yeah.
So I thought compaction actually increases the pressure.
Yeah. Yeah.
Okay.
Yeah. So, yeah, but this is what they used to do in industry.
Okay.
So this is one of the big, well, we're going to this now. Were they speaking about coal or general
I think
biomass?
Francisco was talking about different biomass. And then Han, I'm not sure what his conclusion were, but he was looking at peat.
Yeah, that's the thing, that this was for coal, and they used to compact it.
That's true. Like compaction make the accessibility.
Of oxygen.
Yeah, that's.
So
Okay.
the thing we can discuss this later also, but the thing is that you have 2 factors here. One is that by compacting you are reducing the oxygen access, so you are making more difficult the ignition, but you are increasing the density, so you are increasing the easiness to spread. Like it is easier to, if you have 2 particles, it is easier to ignite this one from this one if they are in contact
Yeah, exactly.
than through the air, because you have to take into account more. So you have these 2, but they observed that in coal,
Okay.
the other one was more important, and it was a very typical way of storing coal to just compact it.
Is that because the more you compact it, the higher tendency is to like explode or react? Because I would have imagined that obviously on one extreme, if it's really far, the particles are too far apart for any explosion to happen. But at the other extreme, you basically make a really solid and a solid kind of solid explode if in the extreme sense that oxygen can't penetrate at all. I imagine that in practice will always be in between these two extremes because you can never compact it so much at no oxygen
I mean,
access.
you are speaking
But
about
It's more fundamental
piles.
question than
Yeah.
a practical one.
Yeah. So what they saw is that it didn't go very deep into this. If you have big piles and you compact it a bit, or not like you don't spend a lot of money on this.
Yeah.
If this is the way of thinking on it. So you don't buy a super machine that can really compact it. You just compact it a bit, and by
Yeah.
reducing it, it was,
Okay. So it's in the spot in between
Yeah.
the two.
Yeah.
Okay.
Yeah? So, somebody said, okay, so we're gonna do the same for biomass. Before Francesco did his thing and he discovered that it was not the same. So again, I really like definitions because I like to, I'm not English mother tongue, so I like to focus on what we are speaking. Biomass is defined as the organic matter used as a fuel, especially in a power station for the generation of electricity. Now, think, how many materials can you think with this definition? Yeah, how can you think that you can define flammability parameters of biomass? Like, it is not possible, it implies a lot of things. So we, and this is what we have done until now, more or less. We started with this project with Lois Register, and we did thermally dried sewage sludge, and we studied how different parameters influence the flammability of dust. Sorry for the quality if it is not very good, but I didn't have the original ones with me, so they are just from the paper itself. So we developed all these, and this is chemical composition, this is the particle size with the minimum ignition temperature in a layer, minimum ignition energy, and induction temperature, and some other parameters with volatiles and ash. Well, this was my first paper on my first proper research. I expected much better correlations because I thought that everything was amazing and the lab everything works and whatever. But it didn't, obviously. But they were not that bad, actually. You can see some correlations and you can see some things here and you can see some lines and you can see some tendencies. So it was working as I expected. So by increasing the particle size, the minimum ignition temperature of the layer was increasing because it was more difficult to ignite the particles, and everything was more or less as done for the cores. The first surprise that we got was when we were plotting in this graph, because all of them have activation energy of less than 79, which was like a threshold for cores. Only the very self-ignition, the cores with a high self-ignition tendency had less than 79 kilojoules per mole. In this, all of them had it. So the first thing that we were discussing was if the activation energy was a good parameter to study. Some years later, some other PhD students are working with Javier, and they are speaking about this. And they are also speaking about if we are grown on the way of calculating the activation energy. And we should then continue using Q-means, and some people, there is apparently some thermogravimetric analysis that can get it in a different way, and kinetics, and I'm not very into this, but I don't know if the answer is still that the activation energy doesn't work that good with biomass, or that we need to change it. I guess that probably Han knows more about this than Megan. It is there, yes, and there is a discussion there, and some people that works with this are really trying to get into it. So, it was my first paper. It was not perfect, but I got some correlations, everything was nice and fun. And then I went for biofuels, and then this was a disaster. Everything was going upside down, nothing was in the same way, correlations were in the opposite way. There's not even a line anywhere. It was very confusing. So here is where we saw the differences between coal and biofuels, and we started thinking on how to treat it and how to do it. And this is the same graph that we had before. So it was a thesis. You know how this is. I couldn't go into everything, every parameter, and check everything. But something that we did was to study the compaction of small layers. We were compacting them and putting them in a hot plate and checking the minimum ignition temperature of these layers. And we observed this. We observed that in the x-axis you have the difference between no compacted and compacted ignition temperature. And we saw that it is not only that in this code, for example, code 2 doesn't have any difference. There are some other parameters that don't have any difference. It was not only this, it was also that by compacting, sometimes we were promoting the ignition. Which, I didn't expect that at all. Like, it was not only no influencing, it was that it was just the opposite of the goal. And it was very weird. And then there is a lot of work behind this, there is a lot of thinking, there is a lot of people looking at this. I think that the main point is that we're working with particle size. And it was okay, because we had, so in particle size we use parameters like D10, D50, all these parameters, specific surface area, all these parameters are based on the fact that the particles are round or almost round, or you can assimilate them to a round shape. What happens is that biomass is not like that. So we are using parameters that are not what we need to do. And this is an example of some biomass shapes, and there is no solution for it. I would like to tell you what to do, but there is not a solution yet. They're trying to look at parameters, they are speaking out different possibilities, they are speaking out particle shape, but there is not. So we started doing these student projects that the NFPA has. They give a small funding for some NFPA projects. And we got one with Inger Maria Hanebust, that was doing her master's thesis with me. Some of you met her in Vienna last year, and she was there with me. We have written this report, that you can see there in the top, influence of particle size and moisture content of wood particulates on deflagration hazard, which is online if you want to take a look. Their idea was that they have a standard, and they wanted us to take a look at it. The standard is the NFPA 664. It is called the Standard for the Prevention of Fires and Explosions in Wood Processing and Woodworking Facilities. And the standard is very long, and they speak about many things. The thing that they were asking was, we have this paragraph there. Do you agree with this? It says the flammable dust, wood dust, is any dust that will propagate a flame front, thus presenting a fire or explosion hazard when suspended in air or other oxidizing medium. Wood particulate with a mass medium particle size of 500 microns or less with a moisture content of less than 25% are considered deflagrable. So, I was not happy with the definition, but since it was just an opinion, we started digging into it. And the first thing that we tried to do was to collect some data. And we went to the internet. And I expected something like lots of numbers and lots of crazy things and lots of... But actually what we got was this. I know that you don't see it. It is not important the numbers that you can see. The important thing is that you see all the gaps and that the table itself, it is only 2 pages and a half in horizontal. I was very confused with this. I really expected to have like one of these tables that you can be working on for days and days and days. But apparently industry is not interested in having it, or we know that they are measuring this particle size because the standard says it. The thing is that they are not making it available for the rest of the people. So not only this, if you go into the top of the table, there are many parameters there, which means that people are not using the same parameters to determine the particle size. So how can I compare things that are not measured in the same way? So we don't know how they are measuring it. Something that I have also observed afterwards, and I have to say that it happens in my papers also, is that we don't even report with which equipment we are measuring the particle size. I have papers where I haven't said it, or the method, or the particle size is this. But it is obviously not enough because there are a lot of ways of measuring particle size. Like a lot of ways of measuring particle size. And we have observed that depending on the methodology that you use, you get different results. So how can I compare things like this? Why they are not publishing it, how they are doing it, with what equipment they are doing it, when can be also important, where they are doing it. We don't know any of this because it is just confidential, I guess. So what is what we need and what the future trends I expect? I define it as a triangle because it is the easiest way of doing things. We need more data. We need people to understand that data should be available, and we need to have it, and we need to be able to work with it, and we need to be able to have a database where people can go. We need to define a common methodology that is gonna be for everybody and that everybody is gonna use it, and so I can compare my things with your things and they are actually comparable. But the most important thing and what I'm really trying to do and what I put in the top of the triangle is that we need communication. We need to be more open. We need to stop trying to be the first ones doing everything, so we just keep everything from everybody, or we don't tell things, or we don't. It is not gonna work like this anymore. We need information. We are wasting a lot of time and we are wasting a lot of resources by not communicating our errors, for example. We should be able to go to the lab, do something wrong, and say, hey, I have tried this. Don't try because it is not gonna work. Because then you can save weeks of work to other people. And with all this, in my fear, in dust explosions, we will then get a safe working environment. So in conclusion, just to finish with this, I hope that you have learned something about dust explosions and what we do and all this, and we can speak about this more and more. But what I would like you to take home today and to make like the main line of what I was saying today, and that you can tweet and whatever, is that the world is continuously changing and we need to move with it, and we need to move in a safe way, always. We need to ensure safe places for all humans, and this includes ensuring safe working places. For this, we need to communicate, we need to contribute, and we need to cooperate. And after this is when we can start speaking about what analysis we want to do. Just follow me in Twitter, I'm glad. And this is my email if you know, you have it, but just in case you have lost it or something, just